Algo Solver LLM Challenge uses 5 increasingly difficult mathematical algorithms to produce a sequence of numbers. Then we pass the first 10 number to an LLM and let it think about it to try to predict the original algorithm. And if it fails at the first attempt, then we give it more numbers from the series, essentially allowing it to predict the underlying algorithm. And then we actually save the results for each model that we are testing separately. And also we form a model comparison table here in my latest test with all these models. O1 Mini actually came out on top. O1 Preview came in second, but if you run this long many times, O1 Preview should win, actually. We've also tested GPT-4o. Let me go ahead and actually play you the sped up video and then we'll run this. So here's a sped up video. This model comparison.txt actually updates in real time. As you can see, we're running the test one after another for each model in parallel. We are trying 3 times per model. And in this case, O1 Mini was able to solve all 5 of the algorithms, meaning it was able to predict an algorithm which produces the same sequence of numbers. We test them with 100 numbers of the sequence that is generated using both the original model, original algorithm, and the predicted algorithm. It also saves the progress for each model. For example, here, Cloud 3.5 Sonnet, for example, failed in the first time around. So each model's progress has been saved. We also save the winning algorithms here, for example, for each one that they have, whichever was predicted. So I built this in iteratively, and all the source code for this will be available at my Patreon if you do download it. If you do become a patron and download it, you'll find 8 files there. We will be reviewing the code for the final algorithm, which runs everything in parallel and updates the model comparison txt in real time. But I will personally actually walk you through how I thought about it, and then I will let my AI code explainer to review the final file. Let's go ahead and run it just so we can see how this works. When you first run it, you get an explanation of what is going to happen, and this will be executing code auto-generated by LLM, so we do have to accept this. And then we start the testing of the algorithms. They're all running in parallel right now, and we created a new run, and for each one, we will be saving the progress report. As you can see, as it becomes available, we'll save. For example, if you look at the Gemini Pro 1.5, it failed the first test, moved on to the second one, and it succeeded in the second test. Now, if you go to model comparison, as the results become available, we'll actually update this in real time. Usually speaking, O1 Preview should be the slowest because it does use a lot of reasoning tokens. So the video that we've seen was a sped up version of this. As you can see, O1 Mini does very well. Also, it's fast. GPT-4o doesn't do that bad either. Okay, so I won't run this, and I don't want to waste your time, as we have played the sped up video anyway, so I'm just going to go ahead and kill it and roughly talk about how I thought about implementing this. So at first, I just asked Cursor to generate a function that's going to generate a complex series. Let's run this real quick and see what we're talking about. See, this function generates the series, okay, and it uses this algorithm to do this. Takes the previous number, squares it at current position, then mods it by 100. If the result is even, averages it the previous number. If the result is odd, multiplies it by 3, adds 1, then divides it by 2. Collatz-like operation. And essentially, this just prints it. So this was actually pretty rough on O1 series of models. I actually got this. I actually just copied this and pasted it into ChatGPT just to try to get him to predict the next number. You can actually experiment like that. It was quite a lot of fun for me. But this was very difficult for them to figure out, actually. In none of my tries, they were able to figure this out. So I created a medium strength one, but essentially you get the idea. You just create a function which generates a series based on some kind of algorithm. And here, if you look at the algo solver simple, all we're doing is we have a function that is going to generate an algorithm, a simpler one. Essentially, we double the next number and keep the number bounded by moduloing it by 100. We give it a seed because this number is going to take in how many numbers to produce in that sequence, and a seed. Seed's going to start 1, an initial length of series, right? So essentially, we're passing this to the model. As we can see, this is our prompt. Given the series of numbers, write a Python function that can generate the sequence. The function should take in parameters n for length and seed for starting number. And then we execute that, and we compare the first 100 numbers. So this is a pretty robust comparison for a lot of algorithms. Essentially, on the fourth one, I made it iterative so that you can actually try again and again, and we give it some kind of feedback. And then I added the list of different types of models to try, but this runs the models, the tests in sequence. And then I made so that each test for each model runs in parallel. I also created the algorithms here that you can actually ask Cursor to create more algorithms. The first one is the doubling. Second one is Fibonacci with modulo, alternating powers, prime factor sum, and collatz inspired bounded. And here are the algorithms actually. So we have a single function essentially, and you can pick which algorithm by passing a parameter called algo number. So this runs actually for each model, the 3 tries or 3 tests in parallel. And then I wanted to make sure that we can use Open Router so we can test such as for 5 billion and Gemini Pro from Open Router. And then but this one, if you run the 7th file, it's going to update the table at the very end, the model comparison. So to make it funner, actually, on the 8th one, which is the exact same as the 7th, which actually updates the table in real time, as we have seen. So this is essentially it. Like I said, you can download this from my Patreon. This is a really interesting test. If you take a look at the results, like DeepSeek coders didn't do well. Essentially, the models should do well, did well, except 3.5 Sonnet was only able to solve 1, for example, in this iteration. So this you can modify, and I think it should be useful for you to test different types of models. It should be easy to modify as well. So now I'm going to let my script, the AI code explainer, explain the 8th file, which is quite long at almost 700 lines of code. And if you do become a patron at the architect level, you can actually download the AI code explainer as well. So let me know what you think, and I'll see you in the next video.
This part of the code handles the initial setup and configuration. It sets up various imports, constants, and data structures that will be used throughout the code. For instance, it imports necessary libraries for API interaction, data handling, threading, and more. The model client data class is introduced to encapsulate the data needed for each model client, making code handling cleaner and more manageable. The configuration section includes constants for retries, series initialization, model specifications, and timeout settings that control how the algorithms will be executed and tested. The confirm execution function is crucial for user safety, as it warns that the program will run potentially unsafe auto-generated code, requiring the user to confirm this action. This ensures that users are aware of the risks involved before proceeding, adding a layer of responsibility protection for the program. Think of it as your code's way of saying, "Are you sure? You trust me, right? We can do great things together, or maybe something wild." The initialize clients function is responsible for creating connections or clients for each AI model specified in the models list. It distinguishes between regular OpenAI models and Open Router models by checking for a / in the model name. This distinction dictates whether the client needs different connection settings, such as base URL or specific headers, necessary for certain models. By encapsulating the client creation in this function, our code remains clean and modular, making it easy to maintain or adapt if new models come into play. Think of this as a backstage setup where each model is given its own dressing room, so they're ready for the main stage performance later. This ensures our models have all their makeup or API configurations precisely as needed. The Generate Complex Series function embodies the mathematical heart of our program, generating numerical sequences based on one of 5 different algorithms. This function takes parameters for series length, seed value, and algorithm type, delivering a versatile mechanism for sequence creation. Each algorithm represents a unique method of number progression, whether it's a simple doubling method, a Fibonacci-inspired approach with mods, or a more abstract variation involving prime factors or Collat's conjecture-style operations. This variety allows you to explore different mathematical terrains, turning simple number generation into a series of intriguing puzzles. With great power comes great mathematical fascination. Incorporated within each algorithm is careful logic to ensure numbers remain bounded within set limits, adding an element of predictability within the chaos. It's like being a numbers wizard, casting spells that are mathematically bound to not go out of control.
Now, listen to me, I've been trying to code, and I like coding. The fact that I can code and make things happen, but how do I do it? I mean, fast with AI. I'd heard about it. It's easy. So I came across 1000x cursor course. And that's great, it just made everything super silky smooth. It just worked. I'm telling you.
1000x your coding.
This function, Create Run Directories, is dedicated to organizing the workspace where model outputs and results will be stored. It creates a new directory structure for each run of the solver based on the current timestamp, providing a unique space for output without clashing with previous runs. The function systematically generates a base directory for all processes, a winners folder for storing successful model outputs, and individual directories for each model. This organizational step is crucial for maintaining a clutter-free environment, allowing easy retrieval and inspection of results. Essentially, it's like tidying up your desktop before starting a project, only this time it's for neatly storing your algorithm-solving adventures. Time waits for no code. The timeout decorator is responsible for capping how long a certain function might run. It achieves this by using Python's threading capabilities to execute the function in a separate thread, thus allowing the decorator to monitor its execution time. If the function exceeds the specified time limit, the decorator will stop the thread, effectively saving you from ending up in the pits of infinite processes. It also cleans up any temporary resources or garbage that might have been created during execution, showing off some stellar housekeeping skills. This feature is especially important when dealing with AI models where execution could potentially hang due to complex computations. Think of it as a kitchen timer for your code, making sure nothing stays on the stove longer than necessary and preventing any accidental fire alarms. The Model Results class and Test Model function work together to evaluate how well a given AI model performs on the number generation tasks. The Model Results class keeps track of the successes, failures, and time taken for each model during tests, along with a method for sorting these results. You can think of it as a scoreboard, only instead of basketball, it keeps track of algorithmic prowess. The Test Model function orchestrates the testing process for a single model. It measures the model's performance by iterating through algorithms, making attempts, and logging results. The function updates a comparison table with results, ensuring progress is documented and wins-loses are clearly displayed. By putting models through these paces, one at a time, the function ensures each contender has its fair chance to shine or crumble under the weight of algorithmic challenges. It's much like a science fair, where each model presents its projects or sequences in hopes of winning a prize. The Solve algorithm function is the mastermind orchestrating the grand testing event. It initializes everything we need, directories, models, and logging for the entirety of the algorithm analysis. Think of it as the musical conductor gearing up to ensure all instruments or models play their parts in harmony. Once setup is complete, it applies parallel processing, utilizing a thread pool executor to handle multiple models at once, allowing them to be tested efficiently. The results are collected, sorted, and displayed in a neat comparison table, detailing solved algorithms, attempts, and execution times. The results capture performance metrics and save them for future reference. Really, it's like a complex choreography where each model dances its algorithmic routine, and Solve algorithm makes sure nobody misses a step, ensuring everything runs like clockwork. Or rather, like a perfectly timed algorithm. This is the script's entry point, akin to rolling out the red carpet for the execution to commence. Within this main block, the code first prints initial messages in gloriously colored text to delineate the testing phase and showcase sample sequences generated by each algorithm. Following this prelude, it calls the solve algorithm function, kicking off the process of testing models against the tasks set by these algorithms. This setup ensures clarity for anyone running the script, showing them what the program is about to do before diving into execution. As ever, it maintains user transparency while setting the stage for a systematic exploration of algorithmic capabilities, or, as we like to imagine, releasing little digital critters into an arena to see how they perform.
I would like to take a moment to talk about the benefits of becoming a patron. As some of you may know, in the last year and a half, I've spent 3,000 hours, over 300 projects. As a patron, you will have access to all the code files so you can get inspiration and iterate quickly. Another benefit is that you'll have access to all my courses. And my most recent and most proud one, the 1000x Masterclass, teaching what I've learned on how to code fast and efficiently. Also the Streamlit course and the Fast API course. In my Patreon, I also have tiers in which you can connect with me one-on-one. Check those out as well.
Now, listen to me. I've been trying to code, and I like coding. The fact that I can code and make things happen, but how do I do it? I mean, fast with AI. I heard about it. It's easy. So I came across 1000x cursor course. And that's great, it just made everything super silky smooth. It just worked. I'm telling you.
1000x your coding.